I'm Chun-Hao To. I'm a grad student from Stanford, and it's my great pleasure to be here to present my work on cosmological constraint from cosmos, galaxies, and weak gravitational lensing. Okay, so a bit of motivation. So the main motivation of this work is to test the lambda-CDM cosmological model. And we all know that this model has been extremely successful, right? With just 6 parameters, it is sufficient to describe almost the entire history of our universe. Perhaps the most obvious success of this model is its ability to describe the data of the CMB, which is the light from the universe when the universe was extremely young. It's about 380,000 years old. So here, I'm showing you the data from the Planck satellite. So the red dot with the arrow bar is the data, and the blue line is the fit from the model. So you can see that despite the fact that the data is extremely constraining, the model can describe the data pretty well. However, there are still many mysteries remain in this model. For example, in this lambda-CDM cosmological model, we know that 2 dominant energy components of our universe is in this very weird form called dark energy and dark matters, and we still don't know what's the nature of them. Second, so we have made a very precise measurement of the early universe by using the CMB observation. If we can make extremely precise measurement like what we did for the early universe, but for the late-time universe by these local galaxy surveys, then can the same model describe both the observations of the early universe and the late-time universe simultaneously? And these questions motivate a lot of wide imaging surveys, including currently DS, HITS, HSC, and future LSST. Today's talk, I'm going to be focusing on the Darkening Survey. So this is the 5,000 square degree survey of the sky, covering in 5 different filters, observing for 5.5 years. Today's talk, I'm going to be focusing on the data acquired from the first years, so from the first season of the observation. So it's covering 1,500 square degree down to 40% of the depth of the full survey. And all the data of today's talk are already released. In Darkening Survey, we have 3 probes of the large-scale structure of our universe. So first, we have weak gravitational lensing. So this is a measurement of the coherent distortion of the Big Bang galaxy shape. And we have 2 bias tracers called the galaxy positions and the galaxy clusters positions. From these 3 from these 3 large-scale structural probes, we can construct 3 cosmic density fields. Right? For the weak gravitational lensing, we can use it to construct the integrated matter density field of our universe. So it's shown this here. Then from the galaxy position, we can construct the galaxy density field and also the galaxy cluster density field. So what's today's talk about? Is about, so from these 3 cosmic density field, we can construct 6 2-point correlation functions from these 3 cosmic density field, right? So it turns out that this is all the 2-point correlation function that you can construct from the 3 density field. So today's talk is about a joint analysis of all 6 2-point correlation functions and the cluster abundance, and we analyze them simultaneously and consistently. A subset of these combinations focusing on the galaxy positions and the weak gravitational lensing and the cross correlation is called the 3x2-point analysis, and this has been extremely successful and promising. So here is the data from the DS year 1 analysis. So the blue contour here is a result from this 3x2-point analysis. So here the y-axis is the SA. So this is the measurement of the amount of structure in our universe, and the x-axis is omega m. So it's the amount of matter density in our universe. So here you can see that the result from the DS is shown as the blue contour, and this is the 1 sigma and 2 sigma contour. The result from the Planck satellite, which is the observations of the early universe, is shown as the green contour. So you can see that the contour size is comparable with each other, meaning that this local lensing survey are already approaching the accuracy that we can get from the early universe. Now you might ask why galaxy clusters have not been combined before, and this is mainly due to 2 reasons. So first, the DS cluster fiducial analysis and other cosmological probe in the DS are intention. So you can sort of see this in this plot here. So here the y-axis is again is a sigma A. So this is again the measurement of the amount of structure in our universe, but with slightly different linear combinations. So the contour size is and the direction is slightly different. But the x-axis is the same. This is omega matter. So this is the amount of matter in our universe. So again, the ray contour here is the result from the 3x2-point analysis. So this is a joint analysis of galaxy clustering and weak gravitational lensing. The DS cluster fiducial analysis is shown here. So this is a joint analysis of cluster abundance and cluster lensing. So you can see that these two contours are in roughly 2.5 sigma tension. And I want to highlight that this tension is actually pretty significant because these are the two analyses on the same survey. So they are highly correlated. And because they are in tension, so it cannot be combined with other cosmological probe in DS. And the second reason is the analysis, the way the analysis is done, make it hard to be combined with other cosmological probe in the same survey. And I'll comment on these points a little bit later in the talk. But the bottom line is, in this work, we solve these two problems simultaneously. Okay, so but before I move on, I want to first convince you why you should care about optical cluster cosmology, which is the main topic of this talk. And these questions can be broken down into two parts, right? So first, why you should care about the galaxy clusters, and second, why you want to find them optically. So for the first questions, we know that the galaxy clusters are associated with the so it's the most massive it's the most massive bounded object in our universe. So if your universe have more structure, then you will have a larger inhomogeneities. Then you will find more large objects. Then you will find more clusters. So just by counting the number of galaxy clusters, you can use it to infer the amount of structure in your universe. This idea can sort of be seen in the bottom left plot. So here I'm plotting the Covalence function. So the y-axis is the number of clusters in your universe. The x-axis is the mass of those galaxy clusters. And three different colored lines correspond to three different universes with different amount of structure. So from the blue to green correspond to a universe that have more structure. So here you can see that when your universe has more structure, you will find more galaxy clusters. Okay, so for the second questions, why you want to find them optically, and this can sort of be seen in the bottom right plot. So what's plotted here, the y-axis is the limiting mass, meaning that the smallest mass of the object that you can find by using different techniques to detect the galaxy clusters. So the purple line and the blue line correspond to the SD selected galaxy clusters. So this is the way that you can find the galaxy clusters on the radial survey by using Sanyov-Zildovich effect. And the green line is correspond to the clusters that you find in the X-ray survey. So it's a future and actually it's an ongoing X-ray survey called ASIAA. And finally, the orange line and the red line correspond to the optically detected galaxy clusters. So you can see that there are quite significant amount of redshift range that the optical galaxy clusters will select the galaxy clusters that have smallest amount of mass. And when you go to lower mass, and you can see the bottom left plot, when you go to lower mass, you will find more galaxy clusters. So then you can do a weak gravitational lensing by stacking more objects. Then you get better weak lensing mass estimation, and you get better cosmology.
Sorry.
Sure.
Why are the two curves for ACT and SPT different?
So because there are two different instruments, right? So the ACT is the. Oh, you mean? Sorry. You mean?
So ACT has a smoother shape than SPT.
Right. I actually don't know. I don't. Yeah. I don't know why there's a difference here. But yeah, I actually don't know. Yeah. And also this is a slightly outdated data, so I'm not entirely sure whether this feature is actually realistic. Yep. Okay, so before I move on, I want to give a first brief overview on how cluster cosmology is done on the real data, and especially how optical cluster cosmology is done on the real data. And this is actually pretty simple, so just involves 3 different steps. So first, you find the galaxy clusters on the sky, then you measure their numbers. In some bins of mass proxy, then you measure their mean mass. Right, then you can use it to just combine the numbers and the mass. You can use to infer the higher mass function and use it to constrain the cosmology. So first, we find the galaxy clusters on the optical sky using the Raymaker algorithm. So this is the algorithm that try to identify the galaxy clusters by the overdensity of the ray sequence galaxies. So the idea is that most of the galaxies in the galaxy clusters are ray. So when you see a crowded ray galaxies on the sky, they are likely correspond to a galaxy cluster. For the second step, you measure the number of galaxy clusters in bins of mass proxy. And for the Raymaker, we use the richness as our mass proxy. So this is the number of red and bright galaxies in the galaxy clusters. So the idea is that when your clusters is more massive, then it will contain more galaxies inside it. The main challenge, however, is to quantify the selection function, right? So you want to make sure that your cluster finder find all the clusters and not find like some random objects as the clusters, right? That's why we call the completeness and the purity. So we want to make sure that both of these quantities are very high. It turns out that for the Raymaker algorithm, we know we have a very good control on these selection functions based on the simulations and also on the observational data. For the third step is that you measure the mass of the galaxy clusters, and it turns out it's the most difficult part. The traditional way is using, most of the common way to do it is using the weak gravitational lensing. So the idea is that the galaxy shape will be distorted by the gravitational potential of the galaxy clusters. So you can actually measure the coherent distortion of the galaxy shape around the galaxy clusters, use it to infer the gravitational potential of the galaxy clusters, and then measure the mass of them. Traditionally, it relies on small-scale modeling. So basically, you model this weak gravitational lensing signal down to very small scale. For example, in the BSY1 cluster analysis, we model this down to 0.2 H inverse millimeter. And we know that modeling small-scale lensing is extremely challenging, because this is affected by a lot of systematics, such as you don't know what's the center of your galaxy clusters. That's what we call miscentering. And also on small scale, you also have a lot of contribution from the baryon. So you also have a lot of baryonic effect that you need to take into account. For our approach, we only use large-scale information to measure the mass of the galaxy clusters. So before I move on, I want to first define the quantity called bias. So the bias is basically a measurement of the ratio of the overdensity of the galaxy clusters and the overdensity of the matter. So you can sort of think it as a relative overdensity of the objects relative to the normal matter. And in our project, we measure 4 different two-point correlation functions. So first we have the cluster lensing. So this is the cross correlation between the cluster position and the background galaxy shape. And we also have the cluster galaxy cross correlation. So this is the position of the galaxy clusters cross correlate with the position of the galaxies, combine that with the galaxy autocorrelation. And we also have the cluster clustering. So this is the autocorrelation of the positions of the galaxy clusters. But here, the bottom line here is that each two-point correlation functions are proportional to different powers of the bias, right? So just by combining these 4 two-point correlation functions, you can get a very reliable measurement of the cluster biases. And why we want to measure cluster biases? It's because in the simulation, we know that cluster biases provide information of cluster's mass, right? So here is a plot from the simulation. So the y-axis is the bias of the galaxy clusters, or in the simulation we call it dominant halos, as a function of halo mass. So here you can see that when your object is more massive, then it will have more bias. So just by measuring the bias, you can use it to infer the mass of the mass of the object. However, now you might say, wait a minute, we know there are secondary Hale biases, and this is people usually call this assembly bias. So the idea is that the cluster bias not only depends on the cluster mass, but also depends on other local properties of the galaxy clusters, right? So the idea can sort of be seen in the bottom two plot. So these two different samples, the red sample and the green sample, have the same mass distribution, but they have different concentration. And here you can see that because they have different concentration, they actually have different clustering property, right? The red one are more clustered compared to the green one. So the red one have a higher bias. And this will be a problem for us, right? Because if you select the samples based on properties other than mass, for example, here if you select the sample based on the concentration, then it will cause a problem on your mass estimation. Okay, so we know there are secondary Hale biases. Then the next question is, are they actually important for our analysis? It turns out that for the Rainmaker cluster cosmology, we select the galaxy clusters not based on the concentration, but based on the richness, right? So the question we want to ask is whether cluster biases depends on the cluster mass and the richness of the clusters. And if you think about it, this statement is actually pretty similar to the statement that people usually make for the assembly bias. Okay, so now the question is this, and the answer to this question is definitely yes. The cluster bias not only depends on the mass, but also the richness of the clusters. So we need to take this into account, or we will have a problem in our mass estimation. And by the way, we call this, because of this, we call this effect the selection effect. Okay, so we need to take this into account, but fortunately, because we only work on large scale, so this selection effect bias is scale independent, and this statement is actually based on two independent simulations, and also you can sort of expect this from the perturbation theory. And because this selection effect is scale independent, then you can have a relatively simple model to describe it, right? So for example, in our analysis, we only use two parameters. First, the normalizations, and also the mass dependence. So basically these two parameters to describe this additional selection effect. Now you want to ask whether this is sufficient, and this is why simulation validation is very essential for this analysis. But before I move on to the simulation validation work, I want to first give a summary of our analysis. So as I said, our cluster analysis involves 4 two-point correlation functions and combine that with the cluster abundance. So the idea is that the 4 two-point correlation functions will give us a reliable measurement of the bias of the galaxy clusters, and we can use that bias parameter to infer the mass of the galaxy clusters. And then combine that with the cluster abundance, we can use it to infer the cosmology just by Hale mass function. On the plot here, I'm showing you the Covalence Metrics of this project, and I want to say that this is actually derived theoretically. And the reason why I want to show this Covalence Metrics, so first is trying to demonstrate the size of the work. So for example, the components covered by the black box, basically here, as the usually called the 3 by 2 point covariance matrix. And all the other terms are derived in this project, right? And second, the second reason I want to show this plot is because I want to emphasize that we properly take into account all the possible cross correlation between different probes. So we are not treating that independently.
Sorry, could you explain a little bit more how this covariance is? You said it's theoretically estimated.
Right. So this is basically calculated by the Halo model.
Halo model. Because there should be very strong orthogonal components because the lensing and clustering very strongly correlated because you're looking at the same sample.
Yes.
But I don't think Halo model can take into account that effect properly. Because it's very I think orthogonal component become very significant.
Right, exactly. So that's why we can derive that by the Halo model, right? So
how do you demonstrate this is correctly estimating the covalence? I mean off-diagonal component.
Right, exactly. So first of all, that's a very good question. And first of all, we actually compare this with the jackknife estimation, and show that they are consistent. And second of all, we actually use exactly the same method on the simulations, and demonstrate that we can recover the cosmology of the simulations by using exactly the same method that we use on the real data.
Also, you prepare the many realizations from simulations?
No. For just one simulations. But we actually use theoretical covalence metrics, also use that to infer the cosmology in the simulations. And then we can check whether we can recover the true cosmology and also whether the chi-square makes sense, right? So if the covalence matrix is wrong, then your counter size will be different, then you probably would not be able to recover true cosmology in the simulations. And second of all, if your covalence matrix is wrong, then the chi-square distribution so we have many realization, right? So when you do the analysis in many realization, the distribution of the chi-square will follow the chi-square distribution that you can calculate it from the expected degree of freedom. And we check that the distribution of the chi-square are actually basically follow our expected value.
Okay, that sounds very strange to me, but because you are looking at a very nonlinear scale, right?
No. We are looking at so scale greater than 8 megaparsec. So it's kind of semi linear.
Surprising that your model works in such small scale. Okay, maybe I should talk to you later.
Yeah, sure.
Oh, sorry. You said you have many realizations, but just one simulation.
Right. So yeah. So let me take a little bit back. So there are actually two ways to construct a covalence matrix, right? So first you have like 1,000 or like 10,000 simulations, and you can use it to construct the covalence matrix. And here we use the theoretical one, so we calculate this from the theory. And the reason we don't use simulation to construct the covalence matrix is because we only have like 20 simulations. Yeah, the reason I said 10 is because the first 10 and the second 10 are not independent to each other, so you cannot combine them to construct the covalence matrix. But because we don't have enough realization, so we cannot use it to derive the covalence matrix. Yeah, actually for this amount of data vector, you probably need like 10,000 simulations to construct the covalence matrix, which is not doable for this follow analysis.
And by simulations, you mean
Unbodied simulations.
just embodied?
Yeah.
So no simulation for like remember systematics.
You mean construct the covalence matrix or the validation? For the validation, I'll cover it later in the talk, but
Like cluster finding.
for the validation, yeah, we actually have remember. I'll talk about it later. But the statement I made for the embodied simulation is that normally how people construct the covalence matrix is just using like 10,000 embodied simulations and use that to construct the covalence matrix. Yep.
Sorry, make
Sure.
How many data points do you have in total? What's the number of
So it's let me think about it. 1,010.
Okay, so covalence is 1,010 times 1,010 components.
Yeah.
And then
So we have
you said
10 to a 6.
was consistent with your Halo model.
Yeah.
But Japan is known to underestimate the covariance on the large scale due to the underestimation of cosmic variance. Right? And to make this covalence metric to be non-singular, you need to make the touch of the Japan to be very small.
Right. So we cannot compare that to the entire scale. We only compare the jackknife with a series covariance matrix within the scale that makes sense. Because when you have only, I don't know. Yeah, so when your jackknife patch is like 100 megaparsec, then you cannot compare the 100 megaparsec scale, right? So we actually make sure that the scale that we use to compare the jackknife and the series covariance matrix are basically make sense, but it doesn't contain all the scale that we use in the analysis.
You didn't use such a large scale data for this analysis.
No, we use very large scale. We use.
It's large scale not demonstrated.
Yeah, it's not demonstrated to be. Yeah, but right, that's true. Okay, but I actually want to also highlight that for the 3x2 point analysis, we also use the series covariance matrix, and this part is basically validated by another method called we actually generate a bunch of simulations and test the covariance matrix. So at least the Hare model works for this page.
Sure, but you said that the main point of your analysis, you make it to the 6 times 2 point, right?
Right.
So essentially your data point is much larger than the previous analysis.
Yes.
So that's why the estimation of covariance will be a little bit critical.
Yeah, exactly. It's actually pretty hard to make it non-singular. So yeah, it's actually a major achievement in this paper. Okay, I should move on. So second, I want to highlight the main difference between our analysis and the fiducial DESY1 cluster analysis. So there are actually two main differences. So first, our analysis only use large-scale information. The DSY1 cluster analysis modeling the cluster length data vector down to very small scale, and this makes our analysis safe from many systematics, including Baryony effect and miscentering. For the second point, it's actually pretty critical. So for the DSY1 cluster analysis, people do a two-step analysis. So the idea is that you get the mass of the galaxy clusters by weak gravitational lensing, and you model the mass and the numbers, basically cluster abundance, to get a cosmology, right? And now you immediately see that there will be a problem if you want to combine this analysis with other cosmological probe in the DS. The reason is that this weak gravitational lensing of the cluster lensing are obviously correlated with each other, with other probe in the DS. So the mass you estimated from this weak lensing will also be correlated with other probe in DS. But now, once you do a two-step analysis, it's very hard to quantify the cross covariance matrix. Sorry, the cross covariance between the mass and other cosmological probe in the same survey. For our analysis, we do this one-step analysis. So the idea is that we go directly from the data vector to cosmology. So this makes our analysis easier to be combined with other cosmological probe, for example, the 3x2 point analysis. Okay, so now I want to present our first work. So our first paper. Basically, we performed the first end-to-end validation test of a cluster abundance analysis on the cathode level simulations. And the philosophy we take is that we treat the simulated galaxy cathode as possible universe, and we do the same the analysis on the simulated galaxy cathode in the same way as we did on the real data. So what I mean by this is that this is sort of the flowchart of this end-to-end simulation test. So we go directly. So we go from to some input cosmology. We can run through some embodied code. Here we use gadgets to get the diameter simulations. Then we have some galaxy-Hale connection model. Here we use a algorithm to put the galaxies on the diameter particles. Then with this galaxy cathode, we treat this as the real galaxy cathode from the data, and we run through the red mapper, the cluster finder, the red magic, the galaxy finder, the BPZ, the photometric redshift code, and some simplified shape measurements. And I want to highlight that this cluster finder, the galaxy finder, and the photometric redshift estimation are run exactly the same way as they run on the real data. With this, we get the source catalog, source galaxy catalog, cluster catalog, and the lens galaxy catalog. We can do a measurements to get the data vectors. For the input cosmology, we get the covalence metrics. Then we can, with the data vector and the covalence metrics, we can use it to infer the cosmology and make sure that it's consistent with the input cosmology.
So your embodied simulation has a resolution to form galaxy. You don't need to rely on any halo occupation assumption.
So yeah, there's actually that's actually a key point of this AGL algorithm. So the idea is that remember I said that we pen the galaxy on the diameter particles, not on the diameter halos. And the reason is because our simulation don't have enough resolution to have reasonable halos, right? But this AGL's algorithm is actually trained on a very high. So we basically this is a two-step analysis. So first we run a very high resolution embodied simulations. Then we can do we can pen the galaxies on the halos, right? Because the halos not as trustworthy because you have higher resolution. Then we can learn the connection between the galaxy properties and the matter properties in that high resolution simulations. Then with that learned connection between galaxies and diameter particles, we can then pen the galaxies on the diameter particles. That's the key part.
So what this red magic is doing? So it's like assigning some SED to individual galaxies?
No. Sorry, give me a. So for this galaxy catalog, this is so once we have this galaxy catalog, this is a catalog with colors, positions of those galaxies, right? This red magic is actually an algorithm that we choose, that we use in DS to select the galaxies that have a good photometric redshift. So basically, it's basically an algorithm that you perform some color and magnitude cost, but it's actually not that simple. But the idea is that these galaxies have good photometric redshift. That's why we can use it as a lens galaxies.
I see.
Okay, so now, as I said, the main uncertain part in this flow chart is actually this how galaxy and diameter simulation. Sorry, how galaxies and diameters are connected. And depends on how we pen the galaxies on the diameters, our cluster finder might have different properties, right? And we want to make sure that the amount of systematic in our clusters in the simulations well spans the real data, right? We don't want to underestimate the amount of systematic that we might have in the real data. It turns out that one of the most important systematic for optical cluster cosmology is called the projection effect. So the idea is that because we can only select the galaxy clusters by a few color bands, so we don't have a good redshift estimation. And this would cause a problem, right? Because if you have a clusters alone, so for example, here is the clusters. Then if you see these clusters from this line of sight, then there is a background galaxy clusters here, and your algorithm might select some galaxies from the background galaxy clusters, as might identify this as some member galaxies of these clusters, right? So your observed cluster galaxies basically contain three main components. First, you have real cluster galaxies. Then you also have some contamination from the galaxies in other galaxy clusters, but along the line of sight. And you also have some randomly projected galaxies. And because this is the main systematic for optical cluster cosmology, so we want to make sure that the simulations by the way, the simulation we call as then the buzzer simulations. So we want to make sure that the amount of projection effect in the buzzer simulations well spans the data, right? But to measure this, we need to define a proxy or a measurement of the amount of projections in the real data. And in our analysis, we use this the SZ parameter. So the idea is that for each clusters on the sky, you can basically scan the richness, basically count the number of galaxies as a function of redshift. Then if your assumed redshift is the same as the real galaxy clusters, then you will have a large number of the richness. But if you assume the redshift wrong, then the richness will be 0, right? So you can scan through this redshift direction and make this lambda of z curve. And the width of this lambda of z curve is a natural proxy for the projection effect, right? Because once you have a galaxy clusters nearby, for example, this small bump here nearby, then this curve will be wider compared to a clusters living in a clear line of sight. So we can actually measure this SZ number in the real data, and this is shown in the figure here. So how I'm showing here, the y-axis is this SZ, so this is a projection effect proxy as a function of redshift. The black line is the real data, and 3 different colors correspond to 3 different simulations. So for example, the orange one is the one that have least amount of projection, and the blue one is the one that have largest amount of projection. And this, for both of these, we have 10 DSY1 realization. That's why I called that we have basically 20 simulations. But for the green one, we only have 1 DSY3 realization. Okay, so now this is the main result for this simulation test. So here, what I'm plotting here, the y-axis is again the sigma A, so this is the amount of structure in our universe. The x-axis is omega n, it's the amount of matter in our universe. The dashed line is the true answer, so this is the input cosmology that we use to generate the simulations. And the blue contour is the expected DSY1 constraint power. Each gray line is the analysis on 1 DSY1 realization. And the orange contour is a combination of all the gray lines. So the orange contour is essentially saying that if you have a survey that's equivalent to 10 DSY1 survey, then once you do the analysis, this is sort of the result that you will get. And different panels correspond to different Gaussian condition model. The first one is the one have least amount of projection. The second one is the one have largest amount of projection. And here we only have 1 DSY3 realization. So here you can see that it's roughly 2 sigma detection of the some systematics. And because this is not statistically significant, so we calculate that this amount of systematic is not significant for the DSY1 analysis. However, this might not be satisfying, right? Because these 2 sigma levels systematics might be an indication of a problem in our cluster cosmology analysis. So we can actually do better to distinguish between whether this 2 sigma level discrepancy is due to problems in our cluster analysis, or it can just come from some statistical fluctuation. So the way we do this is we do the 2x2 point analysis. So this is a joint analysis of galaxy clustering and the galaxy dancing. And I want to say this 2x2 point analysis has been well validated by many different other simulations. So we kind of trust this analysis. So we perform this 2x2 point analysis on the same set amount of simulations. And the result is shown as the green line here. So the orange line is what we get from the cluster analysis, and the green contour is what we get from the 2x2 point analysis. So here you can see that the 2x2 point analysis basically recover the cosmology that's consistent with our cluster cosmology analysis. So we can conclude that this deviation doesn't come from problems in our cluster analysis, and it can come from just the statistical fluctuation in the analysis. Okay, so finally, I want to mention that our analysis not only we basically validate our pipeline not only depends on the simulations, but we also validate our pipeline by using this simulated likelihood analysis. So the idea is that we can analyze the theory data vector and contaminate that by some aesthetic systematics, and trying to make sure that our analysis is not sensitive to those systematics. And here we test 3 different systematics, and I think I don't have time to go through each of them, but the bottom line is that for all the systematics we test, our result is robust against those systematics.
Sorry, in your embodied simulation, the baryon size, so baryon physics, the way to assign galaxies independent of any cosmological parameter and any cosmological survey, so they have real some way to evolve the baryon to evolve the color of the galaxy in the cluster.
Right, exactly. So that's I think that's the assumption we take. So we basically fix cosmology and basically we assume the galaxial connection and the cosmological parameters are independent with each other. So that's a basic that's the assumption that we take. And I think the uncertainty on the galaxial connection model is large enough, and basically make these assumptions valid. Okay, so I want to make sure I have time to show the main result. So with this validated pipeline, we basically apply the method on the real data, and the result is shown in this paper. So first I want to emphasize that this is a blind analysis. For people not very familiar with this blind analysis, is that all the parameters that I show are randomly shifted while we are doing the analysis, and we only know the real answer while we are near publishing our paper. So basically, we write all the papers without the knowledge of the real number. Okay, so before I said that this is a joint analysis of all 6 two-point correlation functions. So here I want to basically define 3 terms. First, I mentioned that we combine 4 two-point correlation functions and the cluster abundance to do a cluster analysis. So this is what we call 4x2 plus number count analysis. So this is our cluster analysis. And the analysis focusing on the galaxy position and weak gravitational lensing is called a 3x2 analysis. And we first check whether these 2 analyses are consistent. If they are consistent, then we can combine these 2 analyses together to perform a joint analysis of all 6 two-point correlation functions to get the main result. Alright, so first, this is our cluster cosmology constraints. Again, this is the sigma omega m plane. The blue line, the blue contour is our cluster cosmology constraints, and different colors correspond to cosmological constraints from different survey and different technique. For example, it's a bit hard to see, but this pink contour is the result from the SBT. So this is the SZ detected galaxy clusters, and the purple one is the one that from the X-ray survey. So you can see that our result is consistent with other cluster cosmology analysis in the literature, and also our constraint power is competitive, despite the fact that we have smallest survey volume. And this is going to change in the upcoming DSY3 analysis. Also here, you can notice there is one obvious outlier, and this is this green contour, and this is the fiducial DSY1 cluster analysis. So the comparison between our analysis, basically the blue one and the green one, is very interesting, right? Because the main difference between these 2 analyses is that the green contour include the modeling of the small scale cluster lensing. So the comparison between these 2 basically saying that the problem that make this cosmology constraint shift from other surveys is mainly due to the small scale modeling of the cluster lensing signal. Again, there's another very interesting contour here is the black contour. So this is using the SPT multi-wavelength data to calibrate the mass of the Raymaker clusters, but using the Raymaker cluster number counts. So we know that only high mass galaxy clusters have SPD multi-wavelength signal. So essentially, this black contour is saying that when you model the cluster mass for high mass galaxy clusters, there will be no problems in your cosmological constraints. So the comparison between the black one and the green one indicating that the problems coming from the low mass galaxy clusters. So the combination of the blue, black, and green is saying that the reason why this green contour is shifted from other results coming from the modeling of the small scale lensing of the low mass galaxy clusters. Okay, so go back to our analysis. So once we have the cluster cosmology constraints, we can compare that with the 3x2 point analysis in the DS. So the result is shown as the black contour. So here you can see that our cluster cosmology constraints, the blue contour, is consistent with the black contour. And we actually run through our tension metric and find the tension is at 0.024 sigma, indicating very strong consistency. Because they are consistent, then we can combine this analysis together, and this will lead to the red contour. And I want to highlight that the red contour is the first joint analysis of cluster abundance clustering, weak density, galaxy clustering, all measured in the same photometric survey. We find that by adding the galaxy clusters, this leads to 20% improvement on the constraints of sigma A and omega n. And finally, I want to say that highlight that the p-value is good, so meaning that we have good chi-square, despite the fact that we have 2 times the amount of data compared to a 3x2 point analysis. And this is the major achievement for the theoretical covalence metrics. And finally, we want to compare our result with the analysis from the Planck satellites, right? Because this comparison serves as an end-to-end test of the lambda CDM cosmological model. And right now, we know that the tension is at 1.42 sigma level, so there is no evidence for the inconsistency. In the interest of time, I'll skip these slides and talk about a little bit about the future. So in the upcoming DSY3 analysis, we actually do a forecast using the simulations. And we can see, so the black line here is our Y1, so DSY1 result, and the blue contour is our expected Y3 constraints. So you can see that if we don't modify the model scale cut and redshift range, for sure for the DSY3 we can increase the redshift cut. So this will increase the sample size and make the constraint power even better. But without doing that, we can see that the accuracy basically increased by 44% in the upcoming DSY3 analysis. Okay, so now I want to also say that this method is not limited to just the optically selected galaxy clusters. We can also combine the SZ selected galaxy clusters with the optical survey. And for example, this is a focus of the LCC Y10, so the 10 years of LCC observations and CMBS for galaxy clusters by performing the same analysis. And this is the constraints on the sum of neutrino mass and the dark energy equation of state. So the pink contour here is a 3x2 point analysis. So this is the LCC only analysis. And the blue contour is once you add the galaxy clusters detected by the CMBS4 survey. So you can see there is a very strong improvement by performing this method.
Sorry, so this constraint on dark energy, did you consider like a tomography, or how this constraint darkness come from?
Sure. Yeah. So this is we use we actually bin the data in fiduciary tomography bin of the basically we follow the LCC desk white paper. So we actually have several tomography bin for the galaxies and also the galaxy clusters.
So can you do the tomography using your data? It's still too small.
Right. So it's not exactly the same. The reason is because the SD survey can go to higher redshift.
Oh.
Right. So that's not exactly the same. Alright, so now the conclusions. So we in our analysis we build a large scale focused cluster cosmology analysis, and this analysis has many nice features. So first, it is set from small scale systematics, and it can provide a comparative cosmological constraints, and it's relatively easy to be combined with other cosmological probe in the same survey. And we have validated this pipeline on 3 versions of the buzzer simulations and showing no significant systematics. And we also have applied the method on real data, and this is the first cosmological constraint from cluster abundance, weak density, and galaxy clustering. And finally we find, and this is the slide I ignored. So, but we basically find this combination leads to improved constraints on the cosmological parameters, but also the most observable scaling relation parameters. And this is very important for if you want to study astrophysics by using galaxy clusters. And finally, I want to say thank you for my collaborator, and my collaborator are Elizabeth Eduardo in Arizona, and Heidi in she was in OSU, and Daniel Grun and Joe DeRose, and my advisor Risa Weiser, and the DS collaboration. Thank you. I'll take questions for now.
Thank you, Brad. I have 2 questions. You mentioned regarding this the possible problems in this DS first year cluster cosmology. Is one reason is coming from the problems, the frequency measurements at the small scales.
Actually, weak density modeling of the small scale, not the measurement.
Yeah, mass modeling for the small scale objects. Yeah. So can you please elaborate a bit on this problem? What is the problem?
Yes. So actually, we actually haven't found the main reason for the problems, and there are many hypotheses, but we still we haven't identified a single source for their problems. So there are a lot of possibilities. So first of all, it can come from the scale dependent selection effect. Right? I said that we have a selection effect and less scale independence on large scale, but we don't know like how those effects would perform on a small scale. And in the DS11 analysis, we basically use a simulation based model of that selection effect and find that they cannot solve the problems. So we know it can either be the simulation is not perfect, or it can be is due to other reasons. So that's the first one. The second one is that there is a bunch of Baryony effect on small scale. And in DS analysis, what we do is we basically ignore that. And the reason why we can ignore that is that our argument is that we basically assume a halo model, but we leave the concentration parameter to be free. And we are thinking that that parameter will absorb the Baryony effect, but they might not be true, and we need to test that. And this, so the problem for the Baryony effect is not ruled out yet. So there are many possibilities.
Okay, thank you. Second question is about the possible systematics of the red map algorithm. It assumes like a fixed detection aperture, like 2 megaparsec, right? And to my understanding, this systematics also propagates into large scale signals, yeah. For like a misdetection of like a assembly bias and this kind of things. So did you actually account for this kind of systematic in your modeling of the selection effect, or you have no such a problem for this 200 class?
Yes. So for the that's actually a good question. So for the assembly bias, I actually trying to make an analogy that the selection effect bias is basically essentially the same as the assembly bias, and we basically leave that as the free parameter and we marginalizing over that while we constrain cosmology. So I think our research is kind of immune to those assembly bias systematics. For the detection problems, for example, the purity and completeness, we assume that's perfect, and the reason we assume that's perfect is because, as I said, that we have trying to we basically use simulations to try to. So, for example, here we in our analysis we basically run red mapper on our galaxy simulated galaxy catalog, right? And we also have the halo catalog in those simulations, and we can compare like whether the abundance makes sense, right? And what we find is that basically the red mapper detect basically everything that's expected. So we know that the purity and the completeness is good, at least in these realizations. We actually also validate that using the real data. So the idea is that the galaxy clusters have multi-wavelength signal, right? So for example, we try to ask a question like, in the DS footprint, can we detect all the like SZ selected galaxy clusters, which we should detected by red mapper algorithm, and we find that 100% of them are detected by the red mapper. And second, this answered the questions about the completeness. The question about the purity, we basically make an X-ray follow-up for a narrow redshift and richness bin of the red mapper. So we have the X-ray follow-up for red mapper sample around richness 30, and with slightly lower redshift. And we find that I think only 1 out of few hundred red mapper clusters don't have X-ray signal. So you can once those have X-ray signal, indicating that those red mapper clusters are real, right? So we know that from this analysis, we know that the purity is pretty high.
So your the richness limit for your analysis is 30 for this.
Sorry, so can I say it?
For your cluster abundance analysis, you said the richness limit is 30. That's right.
No, our analysis go down to 20, but we cannot actually do those follow-up analysis at 20, but we do that at 30. That's the best we can do.
Okay.
Yep.
Any other questions?
And also, I have one question to make sure if I understand this correct. So you mentioned there's your approach and like a two-step approach in the original DS analysis. So if I understand correctly, the original approach is you have in the data vector you have the richness observable in terms of both photometric redshift and also the reflecting mass. And in your approach, the richness is only a function of photometric redshift. Is that correct?
Yeah, actually not exactly. So for the DSY1 analysis, the data vector is mass of the galaxy clusters and abundance of the galaxy clusters, and the mass is derived from the weak density. For our data vector, we have the weak density signal and the cluster abundance as a data vector.
Okay.
Right. So this is why we call one-step analysis.
Okay. So and you ignore all the small scale effects.
We ignore all the small scale effects.
In the reflecting mass.
Yes, and also the clustering.
And so in terms of parameter estimation, so do you lose any cosmological information if you don't if you use this one-step approach versus the two-step approach, or like the information contained in those data vectors are exactly the same, except for the small scale.
I think for theory point of view, I think the information content should be the same. Yeah. If you do everything correctly. Yeah.
So basically, if you take if you back to the original two-step analysis, if you take out all the small scale frequency measurement, you expect the two-step approach to derive the same cosmological constraint as the one-step approach.
Yes.
Well, what too in the small scale data, you lose the signal.
Yeah. I think what he says is if you only use large scale, but do a two-step analysis, you will get the same answer as what we do for one-step analysis. Like for sure. Like when you make a scale cut, you lose signal, but when you do the same scale cut, then the one-step analysis and two-step analysis should give you roughly the same answer.
So I guess my question is, like, in this sense, you can try to validate whether the large deviation in the two-step approach is coming from the small-scale signal or is that correct? So if you remove the small-scale signal and rerun the two-step approach, and if the like the tension still exists, you can say that it is not due to small-scale. So is it
Right, exactly. So, but I think we haven't done that. But I think once you do two-step analysis, focusing on large scale, you will get a roughly the same answer as what we get here. So, yeah.
So from your simulation, you cannot reproduce the tension. So
Yeah, we cannot reproduce the tension in a simulation. That's why I'm saying that
it's a baryonic thing.
we don't know whether the selection effect in the simulation is correct or not.
Good. Any other final question? Okay, so if not, let's thanks Chun-Hao again.